Thank you, Antoine. Hi, everyone. So I will continue my lecture last time. If you remember, I talked about how you can drive quantum trajectories, and I gave you some overview about the feedback. So today we will see a concrete example, so which is the LKB photon box example, which was about how to we stabilize a photon number state inside the cavity, and also we see some the asymptotic behavior of trajectories. Okay, first, and then we will see how we can define a control in order to stabilize one of the. In fact, if you remember, you have a quantum system. So for the feedback, you have. So here you have some measurement, okay? And here I talk about the filtering, so which is an estimation of the state of your system, okay? So in fact, you have the probe, so which inside your system, and then they become entangled with the state of the system, and you measure one of this probe, and you obtain the information about your system state, okay? So here, so you obtain the dynamics of your system state, and then you have a controller here, so which use this information, which depends. I will call this, for example, rho hat. You have your rho. This is your system, and you have some rho. Okay, the true state, and this is your estimation, so which is the expectation of rho based on the observation process up to time t. Okay, and so this is a function of rho hat, and then you input this. So this is a classical signal, so which could be, for example, a laser, so which is in the classical mode, and like that you can control your system state. So what is important here? So first is to know what is the asymptotic behavior of your system state before applying control. Okay, so today we see this first, and then so this is called quantum state reduction for the case of quantum node demolition measurement. So this is so I will define it mathematically later. Okay, so let me start to talk about these experiments. I think we are already here about this. So I have a movie. In fact, you have the Rydberg atoms, so which are the two-level atoms. So for the box B, you send your atom, and then you can see in the video. So they became in the cavity C. They became entangled with the harmonic oscillator mode, and then and then here you detect. And here you apply your feedback, so which is the amplitude of the laser. Okay. But there is also a problem in the measurement-based feedback, because you need to in real time you estimate your state, and then you apply a control. So this is important that you have enough time. So here is one of the problem of the experiments, but was to first to implement a node destructive measurement, and then and to have a real-time feedback. Okay. So in fact, the dynamics. I start first by driving before talking about this to recall you. I think Pierre already talked about this, so I will just give you a recall about this. So you have, so just go back, I think, to here. So you have your, so here you prepare the Rydberg atom. So I will call this the state of the, because you have here, you have the composite system, so which is the state of the two-level atom and the harmonic oscillator, right? So you suppose that your composite state is is a transfer product of G and of your harmonic oscillator psi. Okay. So I will call this here like this, and then you have a Ramsey zone R1, and then here you have a cavity C R2. I think I like this R2, and then you have the detector. So we will see what is how you can obtain your measurement. Okay, so just very quickly recall this. In fact, here you apply a unitary, so which is UR1. And for the node structure measurement, you suppose that the interaction is dispersive. So it means that the tuning is no zero. And you have a unitary which is applied on your Rydberg atom and the identity which is applied in this slide. So it's sorry. So this is psi R1, so which is psi B, and UR1 in fact is has this form. So question is, so in fact is a rotation theta 1/2 minus I. So with theta 1 some physical parameter. And then here you have your the state. Yes, here you have your state that after interacting between atom and the harmonic oscillator, so psi C. So I will call. So then you have another unitary, so which is UC, which is applying this which is applying psi R1. Okay. And you see, sorry? There is Mrs. Polly. Sorry, we check again. Sorry, I don't know. I didn't notice, but you have some unitary like this, so okay. Here is it better? Okay. So in any case, we don't enter any details, just to give you a general. Okay. So you can check. I think here it is very perfectly, so you can check it. So psi C, so you have UC psi R1 and some unitary UC, so which is acting on the Hilbert space of the emitter and Hilbert space of your cavity. And so this is my okay. So you have some. In fact, you can get your UC by looking at the Hamiltonian of the J coming. So which has this form. So I sigma minus A dagger minus sigma plus A. Okay. And then you can continue like this. So you have psi R2, so which is your R2 identity, so which is applied on psi C. And like this, you can get the whole evolution of your state. So the whole unitary is UR2. You have UC and UR1, so which is applied in your initial state, which was psi B, right? And in fact, here you have the entanglement when you are here, psi C. Okay. And from this, so you know, once you know how you how the evolution, what is the evolution? So then you can get your your state. So you have the whole state. For example, I will call psi after psi plus after all of this. So then, so what are you going to say? Sorry. So you have psi R2, yes. So you have which is G. So which is something like this. Plus if you, before measurement, it's like this. When you measure, so then you project your, right? So if you detect G, so you get, so then I6 psi plus is mg psi over square root of pg, so which is pg is the trace of S psi mg by psi, and so with this probability, you have your state after detection like this, or with this probability, which is 1 minus pg, so you have this, okay? So this is just a recall about this experiment. So about the measurement operator. So I was just in case, so just for you, just a recall. And here, in fact, what you need to know, you need to know that what is the evolution when you apply feedback. So your feedback, in fact, is the displacement operator, so the alpha k. So which is applied. So in fact, you have dynamics. If you write your dynamics for rho, so you have rho k plus 1, so which is the alpha k. How I noted this, mk over the trace, and here you have the minus alpha k. Okay, and okay, so and the alpha k is in fact is a unitary which is applied, so which is exponential minus I alpha h, and your h is I a dagger minus a. Okay. So then you know how the dynamics changes by once you apply your feedback. And here we suppose that so we are in finite dimensional, so you have n max. You cannot have more than n max photon inside the cavity. And mg operator has this form, so you have some physical parameter phi r plus phi over 2 plus the photon number operator. So so you can see from this. So then your mg, in fact, is a diagonal operator. So it's sufficient to here, for example, you have cosinus phi r plus phi over 2 here plus 0 photon, right? And so on. So you obtain your measurement operator, so which is a diagonal here, and ME is also a diagonal operator. And the alpha k, in fact, has this form. So the alpha k is, as I said here, is x also minus alpha h. So you get this exponential alpha k, a dagger minus a. Yes. No, I'm not. You mean if we show this? Mm-hmm. Yes, but I'm not sure if we can show. I think for me, if I remember best, the mm-hmm. Mm-hmm. Yeah, here we suppose that we cannot have more than 9 photons inside the cavity, but maybe it's up. But in any case, I know that here in his quarters, they look at also for the case when we have infinite case. So I'm not sure if I mean we can have also infinite case. So here, so for non-destructive measurement, you suppose that your measurements are diagonal. So here, so we are in this case. Okay, so now I will So I know maybe it's very new for you for feedback, but I try to give you some intuition about what we need to do. If you don't know, for example, the mathematical steps to do, what is your intuition about stabilizing some particular photon number state? You know the dynamics. What is the natural thing to look at? For example, you can look at some distance, right, between your state, current state, and the target. Suppose that you want to stabilize some rho bar. So what is the distance between your current state and this target state? So the good distance, you know, the fidelity is a very good distance between two quantum states, right? One minus fidelity. But here you have a pure state, so rho bar, so which is a photon number state like this. So the natural distance is to take 1 minus trace, right? Okay. Then in this paper, so they proposed in 2009. So they propose the feedback like this. So I will explain you intuitively why such a feedback could work. So in control theory, so we talk about the Lyapunov, but you don't need to know really about it. So you can do everything without knowing what is the Lyapunov, because in fact, the Lyapunov corresponds to the distance between your rho and your target state. And what is important is that, for example, at rho bar, at your target is 0, and for any other they say n, so which is orthogonal to rho bar, so this is 0, so then the distance is 1, right? So the thing that you need to know for now. So we have you define your state rho tilde. Suppose that your state just before the feedback is like this. It's like given by rho, and you want to see what is your rho tilde. So in fact, approximately, if you use the Baker-Campbell Hausdorff formula, so this is approximately for alpha small is given by rho minus alpha rho a dagger minus a plus alpha square over 2 plus alpha square rho a dagger minus a. So this is given approximately like this. So then it's good because you can develop this distance by using this formula. So you have so it's sufficient to look at the trace of d alpha k. I will call rho k plus half. I don't remember if I use it in the notation. Just the state after. So in fact, what is inside? So here I will call it rho k plus half, the intermediate state before control. Okay. So you have d minus alpha k rho bar. So just using this, so you will get trace rho k plus half rho bar minus alpha k trace rho k plus half a dagger minus a rho bar plus alpha k square over 2 trace rho k plus half a dagger minus a dagger minus a. So just replacing this inside, okay? So rho bar. So now So you know that alpha k is very small, and you want this thing should be more closer to with respect to this, right? To the target state, to rho bar. When you apply your contour, you want you can be closer to the state rho bar. So then, in order to do this, so suppose alpha k is very small, so you can approximately ignore this thing, and you can say alpha k, I will get minus the trace rho k plus half a dagger minus a rho bar. Because like this, you have a positive term, and then it's clear that this is greater. The term here is greater than this, right? Before control. So this is why the authors here said they take the second one, so which is T1 trace this expression. But why we talk about switching? So this is the other thing. So because suppose that your rho k plus half is blocked, for example, in some other state which are orthogonal to rho bar. So then you get your contour 0 here, right? In fact, this is 0 when you have rho k plus half rho bar or any other the photon number state nn. So that is why that we say, so here when v rho is less than 1 minus epsilon, so when so v rho is less than 1 minus epsilon, so it means that we are yes. So here if we are very close to the bad attractors, so then you take this argmax of, and this is very natural, so because you want to maximize the distance between this and rho bar, right? So when you are close to the bad attractors, so attractors, because there is a fixed point of your dynamical system. So you have some rows. So how I can call it? So n, the state nn. So which is so for n different to n bar. So if you take this control, so this is a 0. In fact, here your control cannot make your distance closer to the target. So then that's why that we introduced this, okay? So so this is just intuition about kind of the feedback that you can get. And here in this theorem, so they showed rigorously that you have.
Sorry,
yes.
So could you remind the UN where it UN is what? It's the alpha. How does the UN appear in the feedback?
Oh yes, through alpha and so
it's alpha n?
Alpha n.
Okay,
okay.
Yeah.
Yes, thank you. So here you have alpha n. Thank you for correcting. So then, okay. So then here you have some technical things that you need to respect in order to show the convergence. Okay, towards some rho bar. So so in fact, if you look at this paper, so it's, yes.
Maybe just before you move on, maybe this goes back to Howard's question, but so it seems here like n max is really a technical. It's to allow the proof to be in a finite dimensional Hilbert space.
Yeah, for the proof, isn't it? Yeah.
Not so much a physical thing, right?
Yeah, exactly.
That probably the.
Yeah, even for the proof, Pierre has worked in infinite. So
yeah, probably it's hard to bound everything since.
Yeah, exactly.
Okay.
That's sure. So the proof, if you look at this paper, is quite difficult. In fact, the ideas comes from the other paper, so which is in continuous time, so which is the paper of Van Handel. Sorry, Miraimi and Van Handel. So in 2009, okay. So, but they look at in continuous time. So it's a science paper, and the idea they apply the same from the similar feedback for the discrete time, and the idea is quite hard technically because you need in any case, the feedback stabilization is always not very easy. And here, in fact, the idea is to show that in the first step, so you need to show that when you are very far from the target, you can, the trajectories, they can achieve this state, which is, they become closer to your target in one step with probability 1, okay? And the second step, so you need to be sure that the trajectories, they don't leave your, the closer region. So then that here you show that the trajectories which start here, so which is called closer with respect to this, to the target, will never hit the original set, okay? It's a uniform non-zero probability positive. And then if you have these two, so then if you look at this paper, so they show nicely, so then the trajectories, they converge to the target state rho bar. So today I don't want to talk about the details of the proof, so you can look at this. So I will just introduce, so this is so you have some simulation here, so you have the detection, and this is your control, so you can see that it converges to 0. So here the target is the state 3,3. So in blue, you have the probability to have n less than 3. And in red, you have the probability to have the complement. And the black one is the probability to converge to the target. So you can see it converges to 1. And the alpha converges to 0. So now today I want to talk what I worked during my PhD, so in order to improve and simplify the convergence. Okay, so in order to propose a feedback which can be implemented in the real time. So now let me introduce the problem more generally before coming back to the example of LKB. In fact, you can define the problem for any discrete time case, for any discrete time system. And the idea, if in fact, the important thing when you do control is to construct a good Lyapunov function, right? So here, 1 minus trace, in fact, we will see it was not very good because you need to use more technical theory in the LSI. So here I want to apply some elementary graph theory in order to construct a good Lyapunov function. So it's not complicated. So you can see you don't need to know anything. So in fact, you have the dynamics rho k plus 1, so which is you apply your feedback, so which is a unitary which is applied on the Markov chain, and this is your state of the density matrix that you know, and UK here. So here I change also the notation UK. Sorry. So UK is in fact is a scalar, so which is a controller at time k, and UK is a random probability. For example, in the case of photon works, it was a G or E, right? But you can suppose that you can have different outcomes, and each outcome comes with this probability. And this is the P of M, and you have this thing. So you have this unitary which is applied in your dynamics when you apply your feedback. And that's it. So just you need also to know the superoperator mu, so which is just to simplify, I call it mu. So now, what is a QND measurement? Okay. So you can show that you have the non-destructive measurement when your measurement operators are diagonal in the basis of n. Okay. So this means that you can write mu as the sum of C mu n and n. And you have this constraint, which is identity, so which gives you the sum of this equal to 1. In fact, each term here corresponds to the probability to get the measurement result mu when your system state is in the state NN. And you need also this thing. In fact, if you I go back to this control. So they suppose also this the second assumption here. By in fact, this is a no zero. What is the meaning? In fact, so you need that you have some observability about your measurement result. In fact, if you suppose that you measure in mu, how you can say the state of your system is a state n11 or n22. In fact, you need that the probability to get the measurement result mu when the system is in the state n1 should be different when it is in the state n2. So we will see why we need. I will enter inside the proof. You will see why we need this assumption. So just for now, so we have just these two things that you need to know. And the other theorem that I use, so is a famous theorem, so which is the Kushner 1971. So if you have a xk, so which is a Markov chain, so in the compact space S, if you can construct, v corresponds to the diagonal, so it's a positive function such that the increment of the conditional expectation minus vxk is equal to some function of x, so which is a positive continuous function of x, then you can say the omega limit set omega is included in the following set. So in fact, very nice. In fact, you need to construct, you want to see what is the asymptotic behavior of your xk, Markov chain. So you need to construct a positive function. You need to develop this increment and to check if this is positive or not. If this is positive, and then you can include that the omega limit set of x is included in this set. Okay, so this is very strong and seems not very complicated. So then, but the complicated thing, the part which is complicated is to construct this B. Okay, so let me start to talk about the quantum state reduction. So when we talk open loop, this means that when you don't have the control. So you have the dynamics, which is just you measure, and suppose Q and D, so your measurement is the diagonal. So in this theorem, so we have shown that rho k is suppose that you have your assumption C mu n1 squared different to C mu n2 squared. We can show that with probability 1, rho k converges to one of the state nn. Moreover, you can also give the probability to converge to the state nn, which depends on your initial state between. Which depends on the distance between your initial state and this state nn, which has this form. So okay, so I can maybe just talk about this. See if I think yeah. So what we first we can show. First, I will show that the population, so which is trace of rho k and n, in fact, is a rectangle. Okay, so I will call this the population, so which is Q and K, for example. So this is a rectangle. What is a rectangle? In fact, if you can say that your expectation is constant in time, so you have rho k. If you have some function f, knowing rho k, if you have this equal to f rho k, so then this is a rectangle. Okay. So I will show that the population verify this. So then you have the expectation of trace of rho k plus 1 and n knowing rho k. So what is the expectation? In fact, you have with probability, you get the measurement result to mu, so which is the sum over mu. So trace mu rho k, mu dag over the trace and n, and multiplied by trace, so which is the probability to get the measurement result mu, so which is this thing. So you can see this is simplified, and the sum, because the trace is linear, so you get sum can go inside. So you have the trace of and as this is diagonal in these spaces, so these two they commute. So then everything is good. So you have the sum of mk, mk dag, rho k and n. And this is identity, right? So then you get a trace of rho k and n. Then you have a martingale. So now I want to use the theorem. So in fact, so what is the meaning of this in terms of martingale? I think Pierre talked about this, also about the martingale, sub-martingale, super-martingale. So in fact, when you have a function v which satisfies this means that expectation of v xk plus 1, knowing xk, you know that q is positive, so it's greater than this, right? And this is in fact the term. This means that your v is a sub-martingale. And there is a there's a fact that you can check. In fact, you have a martingale, and if you have a convex function of a martingale, so then you have your f. So have some g of martingale, for example, g. So you have f over g. You can say that this is a sub-martingale. Okay. So in order to use this theorem, so I will use, I know this is my G, so it is a trace of rho k and n, so which is martingale. So I will consider a convex function, and then I will look at the increments, and I can use this theorem. Okay. So I will take this easy convex function x squared over 2, and v I will consider like this. If there was a minus in my theorem, so I just qx is a positive. In fact, this theorem works either you have positive or negative. It doesn't matter. You can see in the proof. Maybe it's not. Sorry, I forgot to correct. So in fact, you can take either a minus of this or plus. It doesn't matter. It is important that you keep the same sign, and then you can use your theorem. Here we said minus f is concave, so then you have this expectation v rho k plus 1 knowing rho k is less than v rho k. And if you look at the increment, in fact, this is not difficult. You need to develop this thing. You get something like this. So this is my q. So and you can check that easily. So this is a square something, some probabilities. So this is positive, okay? And you have minus, so the whole is negative. So then you can use the theorem. So then the omega limit set, in fact, it can be defined by the set of rho infinity such that this is 0, and as it is a positive, the sum. So then each term should be 0. So now, how we can conclude that the 0 of this term is it should be a photon number state. In fact, suppose that you have two different. Sorry, maybe I think here I missed something here in the slides. I will write. So if you look at the 0, so you have trace of mu rho infinity mu dag. So the first thing that you can say that there exists at least one m bar such that m bar rho infinity m bar is positive strictly, right? Because you know that rho infinity is a quantum state, so trace is 1. So then at least there exists one m bar such that this. So then that's why I write the equality over there. So like this. So you have for this m bar I write like this. Okay. So now if you sum over nu, so you have the trace the sum of y square. You have the sum over nu of this. So I will sum at the both sides. And then you get so this is 1, and this is also 1. Okay, so you get C mu m bar square is equal to trace of mu. So you get this. So now you suppose that, but you don't know if there is one. If there is one, so then we are done, right? But then that's why we suppose that there is another one. Because suppose that you have another, you have m bar 1 and m bar 2, such that you have m bar 1 rho infinity, m bar 1 strictly positive, and m bar 2 rho infinity, m bar 2 strictly positive. So if you have this, so you can see from this, so you get C mu m bar 1 square equal to this m bar 2 square. But this is in contradiction with our assumption that I suppose, right? So that is why this is not possible. So then, so it's good. So now you show that you have necessarily the convergence towards the state, one of the states m bar, but you don't know what is m bar here, right? So it could be any photon number state from 0 to m max. And so now you want to precise the probability to converge to m bar. So this is we will use the martingale that I talked about. This the population. I said the trace of rho k and n is a martingale. So then you can say that the expectation of trace. So up to here, you have shown that the probability measure for the rho k converges to this, the sum of Pn delta and n, right? And Pn is the probability to have the convergence to the state Nn. So now I will use the martingale probability. You can say that expectation of trace of rho k and n. So if you know the probability distribution, so you can show that this converges to Pn, right? This is the probability distribution. And you can also use the fact that this is a martingale. So this means that the expectation remains constant at each time. So then you have expectation trace of Nn rho k is equal to expectation trace of Nn rho 0. So then you can say that Pn should be equal to this, right? So which is n rho 0 n. So then, like this, you up to here. So we show that your trajectories, they converge to the state Nn with the probability which is given by the trace of Nn rho 0. Okay. So now, so this is this proof uses the Lyapunov technique. So I want to talk about other proof, another proof in the literature, which was which was done in parallel to this one. So just for your, maybe should be, I think it should be helpful, beneficial. But they don't use the Lyapunov. They don't construct the Lyapunov like this. And moreover, they gave also the asymptotic, the rate of convergence. That is nice. So that's why I would like to talk. So I will consider my open loop dynamics, which is this trace of this. So here I'm talking about a paper from Michel Bauer and Bernardin. This is 2011, and the other one, this is a physics paper, and then it was completed here by Bauer, Benoit, and Bernard in 2013. Okay. So I will just explain the general ideas that they use. In fact, you have, I will just give you some notation first. So the probability to, I will define this probability, the probability of, to get a result mu knowing the state n. So this is a trace of a mu and n mu dag. And they also suppose a similar assumption that I talk about. So it's got assumption for n1 different to n2. Suppose that the probability to get mu knowing n1 is different to probability to get mu knowing n2. So now the question is, what is the asymptotic behavior of rho k? Supposing this assumption, so this is the identifiability assumption of your measurement result. For this, so there's a theorem that you can look. But here I've just announced the theorem and give the ideas to how they prove this. So in fact, they show that there exists so first I will introduce some notation. So you have Q and K. So the population, so which is the trace of NN rho K. Okay. So they show that there exists a random variable. So gamma, for example, such that the limit of Q gamma K when K converges to infinity is equal to 1, right? So then, so in this case, you have the limit of rho K is equal to gamma gamma. And also they give also the probability to get gamma equal n. So which is with this notation it should be Qn0, right? Similar to the theorem that I gave in the slide. So this is the corresponds to the quantum state reduction. And what they prove is different. So in fact they use so the proof. So I just give you some ideas. They use the martingale property first of all. Property of trace of rho K and n. And then they look at the increments and they say that this is a square integrable. So this is the first thing that they use. And also the following theorem, So when we are talking about the asymptotic behavior of trajectory, we should talk about this also, because it's the first work that I'm aware of on this regard. So it's with a pathwise. So ergodic theorem of quantum trajectories. So this is by so Kummerer and Michel. So 2004. In fact, they show that if you look at the César mean of your trajectory, so which is the limit of 1 over n when n converges to infinity of rho k from k0 to n minus 1. So then this is given by theta infinity. So what is theta infinity? In fact, this theta infinity is a random variable. So this is the ergodic theorem. Theta infinity is can be determined by the. In fact, it is included in the set F, so which is the fixed point of your average dynamics. So what is the fixed point of the average? So in fact, it contains the set rho such that phi rho, so the canal, is equal to rho. So the average of the, in fact, expectation of rho k plus 1 knowing rho k, in fact, is given by phi rho k, right? So if you look at the fixed point of this, here they show the other. So then you have the limit of 1 over m, the sum of rho k, converges to some random variable theta infinite, so which is included in the set of the fixed point of your canal. So this is the two things that they use, and they get the result that I announced. And so now I want to talk about the different things that they look at. So I can maybe erase this part. Because why I talk about this? Because next time I will also come back to talk about the rate of convergence, so which is how we can show that we have exponential convergence. So the first work is about QND, and they show that you have the exponential convergence almost surely, and they precise the rate of convergence. Okay, so in order to complete, I should talk. So in fact, the theorem is that, so this is like Benoit and Bernard. So there are in fact two papers, so which is 2011 and 13. They say let n be such that Qn of 0 is different to 0. Okay. So then you can show that one over k infinity of the ln of Qnk Q gamma k. So just remember what is Q. So it's Qn k. In fact, is the population, which is the trace of Nn rho k, right? So if you look at the ratio of Q and K and Q gamma k, and gamma, in fact, is a random variable, so which is selected by the trajectories that the thing that gamma should be any state Nn. Okay? Because before in the previous theorem, you showed that you have selection to this gamma. So now you want to see how fast your trajectories, the other populations, other than the one selected by trajectories, can decay with respect to time. Okay, so that's why we look at the ratio between these two populations. So then they show that this is given by the relative entropy. between the probability generated by gamma. I will say what is this, and probability n. In fact, probability of n is the probability. You want to write the probability of n. So this is the probability to have is knowing the state n, right? So it's a conditional probability. So in fact, they show that this is given by this related entropy. So then this is just to recall what is this? Have mu, probability of mu knowing gamma, and then ln of the probability of mu knowing gamma over the probability of mu knowing n. So here, how much time I have? I will talk about the proof of this, because I think it's interesting. So first of all, they use the fact that you have some relation between some recurrence. In fact, you have Qn. If you look at the Qn k plus 1, so which is a trace of nn rho k plus 1. So you have some relation Qnk, probability of mu k knowing n over pk of mu k. So why this is true? I can write it because it's not difficult. So this is Qnk plus 1. In fact, it's a trace of nn rho k plus 1. So which is mu k rho k mu k dag over trace. So now you use just the fact that your measurement of operator muk commutes with nn. So then you have the trace of muk dag, rho k muk dag. Sorry, just here nn. There's no trace. Yes, okay. Over the trace of this. Okay. Okay, so just here, I can mute this. Here, I put it here. So now, so you know that muk. So nn is a fixed point of your dynamic. So muk nn muk dag over the trace is given by nn. So now you can replace this thing, so which is the dag of this thing, by this product. Okay, so if you do that, so then you will get exactly the equation, so which is Qnk, probability of μk knowing n over pk of μk. So now if you continue, if you iterate this formula, so then you have Qn k plus 1, so which is Qn0, the product of the probability of μk for k prime from 1 to k over the sum of this Qn0, the probability knowing m, we sum over m. So here is Qm. Yes. So then, so if you know, once you know this, so then it's easy to calculate this expression. And if you calculate the expression and you look at the limit, then you will get the then by using the law of large number, maybe I don't have time to enter in details, so you can get exactly this relative entropy, okay? So now if you don't have question, I don't know if you have question, please ask. So I will continue. So I will talk very briefly about the design that we used. In fact, you have these dynamics, and we want to. So maybe just to summarize, because I gave you different approach. So in fact, for now we have shown that rho k converges to NN, and we precise the probability to get the state NN. So now we want to fix one of these, for example, the state n bar n bar, and show that the trajectories there exists a control, and we precise the control such that the trajectories can converge to the state n bar n bar. And so the idea is like this. In fact, this is not always possible in general in control theory. So in fact, you need some assumption on your Hamiltonian. Okay? That is why. So here we talk about. We suppose that the Hamiltonian is connected. If you look at the graph associated to the matrix of the Hamiltonian, suppose that if it's connected. So then here we construct a Laplacian matrix. I'm not sure if you are familiar. In fact, the Laplacian is the matrix which is positive on the diagonal and negative in the off diagonal. And also you have the sum of any rows and any columns which is equal to 0. So why we talk about this is maybe very strange here, but we see it's a very natural thing that in fact we have this Laplacian matrix which is appeared if you look at if you want to restrict your limit set to the state n bar n bar. So this is a Laplacian, so you can check that the sum of any row and any column is 0. So I don't do that. You can check. If you have problem, please ask me now or later. And we assume that, so this is if you have the connectivity of your H, so then your Laplacian is connected, because you can see it's related to the elements of H also. So then you can say that this is also connected. So now we say that if you look at the product of RH sigma equal to lambda, and suppose that your lambda, if lambda is a vector, you suppose that your if you look at RH sigma equal to lambda, and you fix lambda n positive for any n other than the target, and for n equal to n bar, you suppose that your lambda n bar is negative, and also is given by minus the sum of lambda n for any n different to n bar. So then you can show that there exists always. So here we use the graph theory. So you can show that there exists always a sigma if you fix your lambda like this. For a Laplacian matrix, there exists always a sigma such that there exists always a sigma such that it verifies this condition. Okay. In fact, what is the ideas of the proof? You can show that if RH is a Laplacian and its graph is connected, so then the kernel of RH is the vector 1, 1, the only so it's dimension 1, and you have a symmetric matrix, and you know that the image of a symmetric matrix is orthogonal to its kernel. So then this means that any vector, so which is orthogonal to the kernel, in particular the vector lambda, so which verifies that lambda n is equal to 0, in the image. Okay, so then this is a good. So then if this is an image, so there exists always a sigma. Okay, it's a simple thing. In the graph theory is known, very well known. So now, okay, so now I will. So why I talk about sigma? Because you want to construct a Lyapunov, so it depends on such a sigma. And because before, if we look at the 1 minus trace of rho and n bar, I think, if I talk about this Lyapunov. So now I want to introduce some weights in the distance between rho and n, so that I call it sigma n. Okay. And like this, I control the distance between the set rho and n by adjusting the sigma. So this means that, for example, if you are very far from the target, so then you apply more. The sigma should be larger, for example, should be smaller. Sorry, and if you are, because you want to decrease the distance. If you want to if you are very close to the target, so then you can apply a bigger sigma here. So so here why we talk about Laplacian and so on. In fact, if you look this Lyapunov function, and if you look at the second derivative of this function, when you apply the control, the superoperator of the control at the state nn, so you get this, so which is the sum of sigma L, and here this corresponds exactly to the element NL of your Laplacian. So then you have the second derivative, so which is the sum of R and L sigma L and lambda n. So why this is useful? Because like this, you can control the second derivative of your Lyapunov function when we are in a state nn, and we apply the control. Okay. So first you can say we don't know yet we are in a state nn. And so in fact, suppose that you know that your trajectory is converges to a state nn, and you want to apply feedback, and like this you can isolate the set of the limit sets to the state n bar, because you know that the state n bar is a maximum of this function. So I will give you details about this. In fact, the good Lyapunov is a good up to now. No, maybe it's, I think it's more improvement, because you can take this the sum of sigma n and rho n plus some epsilon, and the open loop here. If you remember, when we talked about, let's just come back to this. So this was here. So if you remember, for when we don't have a feedback, we have open loop. So we consider this function, and we show that we have this convergence towards the set nn. So I want to use this open loop because it's useful, because it brings us to the state nn. And by the other term, I can control the convergence to the n bar exactly. Okay. So that is the idea, because sorry. So in fact, you have this sigma n rho n plus the open loop Lyapunov that I talked, and we say that if epsilon is not too large, so I will explain why this is useful. So you can take this control, so which is the argmax of this Lyapunov at UU of rho k plus half. If you take argmax of this as your control input, so then the closed loop trajectory converges to the state n bar. Okay, so maybe so if I come here, so in fact, when we want to use the Kushner theorem, so you need to write the increments of your Lyapunov. So you have the expectation of W epsilon rho k plus 1, knowing rho k, minus W epsilon rho k. So I just detail this a little bit. So you have expectation of epsilon rho k plus 1 knowing rho k minus thank you. So this is exactly the same as over there. Okay. So you have in fact the probability rho k plus 1 could be so this is the first term. So in fact this thing, the probability to get mu knowing rho k, and this is my control that I define like this. So maximum of this function. So your control is argmax of this, right? So then this is defined by maximum of this function. So I will write so p mu okay maximum of w epsilon mu of rho k plus half. And you suppose that you have you fix your interval for your control, because in practice you cannot have any, is bounded. And minus w epsilon rho k, right? So this is expectation of w epsilon rho k plus 1 knowing rho k minus w epsilon rho k. So now I will add a term and subtract it, so which is w epsilon mk rho k minus w epsilon, in fact the sum of p mu mu rho k, right? The superoperator minus the same, so which is p mu rho k and w epsilon mu okay. Sorry, plus and minus. Why do we do that? Because like this you can use why? Because for the first time, so you have sigma n and rho n, right? Plus epsilon and rho n square, right? Over 2, I think. Sigma sum of this epsilon. In fact, I will consider this term, these two together. So I will call it Q1, I think. And you have these two terms, so that I will call it Q2, okay? Q2 over. And use now, this is a martingale, okay? So if you had a difference between these two, so then for the first term is cancelled. So just the only term which is appearing is this. And you know this in the open loop because you studied this before, right? And you know by this. So this is, I will call it Q over OK. So which is Q1, just the other time, plus Q2 rho k. And by the equational term, so you know that the limit set is included in the set where Q is 0. So this means that Q1 of rho k is 0. And Q2 of rho infinity should be 0. But Q1 of rho infinity is 0. And this is, you know that the only state that which verify Q1 of rho infinity is 0 is a set Nn. This comes from the open loop, the previous calculation. So now, if you look at the 0 of this function, so you will replace rho k plus half by Nn. And so you have, if you look at this term, you can say that the maximum of W epsilon u n n equal to W epsilon n n. Now it's good because why it's good? Because if you look at the W epsilon, it has this form. And you know that by the choice of sigma, we say the second derivative so you said the second derivative of this, I will call this W0. And this is W epsilon. The second derivative of W0 of UU and N with respect to the control. When you look at the control 0 is positive, is equal to lambda n, so which is positive for any n different to n bar, and is negative for n equal to n bar. So then this is if your feedback is very small enough, so then this maximum, this equality can arrive only if you have the state n equal to n bar. Okay. So this is the whole idea of our feedback, and here you can see how it looks like the coefficient sigma n. So here we wanted to stabilize the 3 photons, and so you can see this is maximized for 3 photons, and this is our feedback, and epsilon, I didn't talk about this, because you can ask, this is a n bar, so is a maximum of W0. Why it should be remain the maximum of W epsilon? But this remains because you choose your epsilon very small, such that if I come back to my theorem, our theorem, so you have lambda n plus epsilon and this term which is positive. Okay. So then you by adding epsilon, you don't change the sign of lambda n, the change of the sign of the second derivative of W epsilon. Okay? So that is the idea. But so this is in theory. But in practice, we have seen that if you take your epsilon 0, it works also. You can stabilize. So this remains to do. If you're interested, and you have the Hilbert space, so it's just like this. So now I come back to my to the LKB photon box to see how this feedback has been applied in the experiment. So you have, in fact, a Hilbert space like this, and we suppose that theta over p is irrational. So in order to satisfy this assumption, this is our Hamiltonian, and you can check easily that this is connected because it's a 3 diagonal matrix. And you can go from any n1, n1 to any n2, n2. And we take n bar 3, lambda n positive, I said here. So lambda n1 for any n different to n bar. And epsilon is less than, this is in order to satisfy the assumption that I said epsilon should not be too large. You need that epsilon should be small. And okay, so this is good. Everything works good, but there is a problem because if you look at this feedback, in fact, it's the ergo maximum of this function, and this is not easy to calculate, right? So it's very complicated. But for the experiment, it was feasible. So you have because you can use the Baker Campbell, so you can develop your unitary like this. And it was possible to calculate the maximum event. The time scale of the experiment was very short, but it was possible. That is the simulation. So you can see the convergence towards the coordinate 3, 3. So this is one thing. So this is but for the perfect measurement. Okay, up to here. So we suppose that everything is perfect, and we did the development for perfect. But in reality, it's not the case. So here is a thing. I think Pierre he did this, right? So you have, suppose that you have many imperfections in the experiments, and you don't have, for example, one of the possibility for imperfection could be if you measure the state in G, how it could be E, or you have the sample where you have 0, 1, and 2 photons, so which are the distribution given by the Poisson distribution. And in fact, the dynamics, there is a nice paper, I forgot to mention here, is Somaraju, so who was in postdoc here, I think 2013. So they show that you get these dynamics. And okay, so this is our dynamics. So you need to define the cross map like this. And in here is the probability to get E knowing that G. So we have possibility 0 photon, 1 photon, or 2 photon. So you need to correlation between all of these. And these are determined by the physical parameters, so which is the epsilon is the detection efficiency, and eta G is the probability of erroneous. So to get G, if the state was E, and so on. And here you can see the experiment. So you have, and in my paper, in fact, I've shown that our feedback is robust to these imperfections. So here you can see the experimental data, and okay, so you have the G or E, and here you can see the green one is the probability to get 3 photons. In fact, they have observed that with a fidelity of 47%, I think. So you have the convergence towards the three photons. And there's a video. I don't know if you have time to show. Or I guess, yeah. So you have the open loop trajectories and closed loop. And you can see that it works quite well in contrast to the imperfection. So you have so the detection, the distance between your tree and row, and here is our feedback. So when we are close to, sorry, there is no feedback. So this is the open loop. So you can see here you have the convergence to the, this is not deterministic, random convergence towards the photon number state. And this corresponds to the probability to have n photons. With respect to time. And the closed loop. So here the detection efficiency is 40%, eta G is 10%, and there is also delay. And also there is the coherence identified, so it's also you don't respect the QND measurement because there is the photon loss and capture of photon, and so you change your dynamics, many imperfections. And you can see we have quite a good convergence towards the 3-3. So you can see the contour is, when we are far, the contour is applying, and in order to get the state 3-3, right? And okay, that's it. Thank you for your attention. If you have questions.
Yes, thanks, Nina. Are there further questions? So I guess in the last case with closed loop trajectory, there is the feedback stays always on, right, to compensate for photon loss?
Yes.
Okay, I see. Before you had shown that the feedback was going to 0 as you were stabilizing, but I guess it was in the pure QND case, or?
Yes, that's true. But yeah, here is the experiment, so there is not it's not exactly what is corresponding to theory, but in contrast to this is
like here, all of this is taken into account in the theory, or you're basically, are you using a feedback scheme closed loop?
Yeah, I use
that is built from the exact one, and then it still works in the approximate case, in the experimental case, or is the feedback you're using already taking into account all these imperfections?
Yeah, in the feedback that we use is taken in the imperfections. Yeah.
Okay. Okay. Thank you. Are there other questions? I guess if not, let's have a break. We come back at 11:30. Okay, let's thank Nina again.
Thank you.